Today we're going to introduce the idea of a limit. First thing we need to talk about is what are we actually talking about when we're discussing finding a limit. The easiest way to think of limits is limits are just going to be what does your y value equal or approach as you pick numbers or as you get close to some value of x. Now we write that like this. The limit as x approaches, let's say some value c for f of x equals, and then we get some value for that, some number. We call that number the limit. Okay. So really a limit is just what's the y value when you get close to some value of x. So let's start with an easy example. Let's look at this graphically first. So let's say we take f of x is x squared. Remember, f of x is the same thing as saying y equals. So if we look at the graph, we're going to have points at 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. We're going to get a graph that looks something like that. And then we're going to look at what happens, let's say, if we do the limit as x approaches 2 for f of x. So remember, what we're asking ourselves is what's the y value going to be for x values that are close to 2. So if you look at your graph, as you pick a number close to 2, let's say 1.9, we come up here, well, the answer is close to 4. If I pick a number like 2.1, that answer is also close to 4. So we would say then that the limit as x approaches 2 for f of x would be 4. We can also talk about what's the limit, let's say, as x approaches negative 1 for f of x. So if I were to pick a number close to negative 1, let's say negative 0.9, we look up here, our y values are close to 1. Pick a number, let's say on the other side of negative 1, like negative 1.1, we go up and our y values are close to 1. So we would then say that the limit as x approaches negative 1 for f of x would equal 1. Now let's look at a picture that's maybe a little more complicated. Let's say we have f of x as the graph of y equals 1 over x. Well, if we plot some points, we could get, let x be 1, we'd get 1. Let x be 2, we're going to get a half. Then we're going to go to a third, a fourth. If we go back now and do like a half, 1 over a half would be 2. A third's going to put me at 3, so we're going to start to get the idea that the graph's going up there, coming down this way. We could also plot like negative 1. If we put negative 1 in, we're going to get negative 1. Negative 2, we'll get negative 1 half. Negative 1 half, we'll get negative 2. So we should get the idea that we're doing this kind of thing to the graph. So now we see that we've got some discontinuities here. We've got some breaks in the graph. So we might ask, let's start with what's the limit as x approaches, let's say, 2. Well, we've already talked about that when we graphed when x was 2, our y value was a half. So I would expect that if I picked a number close to 2, then the y value for that should also be close to a half. So we could say our limit as x approaches 2 would be a half. We could also talk about what's the limit as x approaches negative 5. So as I go over here towards negative 5, and I follow the graph, I'd see that my y value would be getting close to negative 1/5. So if I pick a number that's smaller than negative 5, I should expect my answer being close to negative 1/5. And bigger than negative 5 would also be negative 1/5. So then I would say my limit as x approaches negative 5 might be negative 1/5. Now we can see that there's some other things happening here. You've got some asymptotes here. We're going to focus later on what happens as, let's say, x approaches infinity. So looking at that, just briefly touching on that, as x approaches infinity, I'm saying as the x numbers keep getting bigger and bigger and headed out here towards the right, what are the y values doing? Well, the y values just keep getting smaller and smaller, so they're going closer to 0. I can also see what happens as x approaches negative infinity. Well, if I pick numbers that are going to the left towards negative infinity, I can see that my y values are also going towards 0. They just happen to be coming from the bottom of the graph. So they're getting smaller, but they're going from the negative direction. So we're going to have like negative 100, negative 1,000. But they're still getting closer, and they're getting closer to 0. Now, the next thing we want to focus on is what happens if I ask about the limit as x approaches 0. This is tricky. If you see, at x approaches 0, it's going to depend on which side of 0 that you're on, what kind of value you're going to get. If you pick a half, the y value is going to be 2. If you pick a third, it's going to be 3. And the closer I get to 0 on the right-hand side, my values keep getting bigger. As I go towards 0 on the left-hand side, my values get to be bigger in negative numbers. So you'd have like negative 5, negative 20, as I keep getting closer to 0. So this time it depends on which side of 0 that I am to be able to tell you what the limit would be. Well, there's a rule that says that if you have to look at which side of 0 you're on and you get a different value for those different sides of 0 or whatever value you're approaching, then we would say in that case that the limit does not exist. Because I have to know if you're on the left-hand side of 0 or the right-hand side of 0 to tell you what the y values are doing. All right, now let's look at this piecewise function and look at some limits on it. Let's say that we wanted to find what is the limit as x approaches 2 for f of x. Well, we want to look at our graph. As x approaches 2, you'll notice that all the y values for values of x that are close to 2 have y values close to 0. So the limit would be 0. We might ask, what's the limit as x approaches 1 for f of x? Well, if we look at x approaches 1, all the y values close to 1 are approaching 2, even though there's an open circle, there's a discontinuity at the ordered pair 1, 2. There's no dot there. If I pick a number that's a little bit less than 1, like 0.9, the y value is close to 2. I'll pick a number a little bit bigger than 1, 0.1, the y value is close to 2. So even though there's no dot there, no point there, or we're undefined at that point, we still say that the limit in that case would be equal to 2. If we look at the limit as x approaches 3, same kind of thing here. We have a discontinuity here at 3, but what we're going to notice is there is a point defined at 3. There's an ordered pair at 3, negative 4. But then we've got this hole here at 3, negative 2. So what happens as x approaches 3? Well, if I pick a number that's a little bit to the left of 3, like 2.9, the y values are down here close to negative 2. If I pick a number a little bit bigger than 3, like 3.1, the y values are still close to negative 2. So we still say the limit is negative 2, even though the y value for 3 is negative 4. Limits are what happen as you approach an x value, not what happens when you get to it. So as you pick numbers close to 3, where are all the y values falling on either side of 3? Now, just like in our previous example where we had an asymptote and something was different was happening on the left-hand side of 0, on the right-hand side of 0, you can also see that we've got the same thing kind of happening here as x approaches negative 1. So if I look at what's happening at negative 1, well, there's something different happening on the left-hand side of negative 1 than what's happening on the right-hand side. If I look at the left-hand side of negative 1, numbers that are a little bit to the left of negative 1, like negative 1.1, the y values are falling up here close to positive 1. Right. So if I look at negative 1.1 and come up here, the y value is up here close to positive 1. But I'll look at negative 0.9, y value is up here at 2. So how can I differentiate what's happening on the left and the right-hand side? Well, we can talk about something called a left-hand limit and a right-hand limit. To show that I want to look at the left-hand side, what I'll do is I'll put the limit as x approaches -1. We put a little negative here, and that's read from the left for f of x. Okay. So that's the limit as x approaches -1 on the left. So on the left of -1, that was the values that we said we're going to be writing here, and they're going up towards 1. And we can also talk about the right-hand side. And we would say the limit as x approaches -1, and then we put a little plus there, and that means from the right-hand side. Okay, so that's read the limit as x approaches -1 from the right. Okay. If I look at the function from the right-hand side of -1, I'm at 2. Now, this is a really, really important concept. For a limit to exist, the left-hand limit has to equal the right-hand limit. So going back to this problem, since the left-hand limit was -1 and the right-hand limit was +2, then we would say the limit as x approaches -1 does not exist because it's different from the left-hand side than from the right-hand side. Okay, next thing we're going to look at is some properties of limits. Now, just hold on. I promise this will kind of all come together. At first, it looks like a lot of mumbo-jumbo, but it comes together and it just makes sense. It's one of those things that go, well, that just makes sense once you get through it. All right, so we're going to say let L, M, C, and K all be a real number. And the limit as x approaches some value of C, f of x, is L. So we know that as x is getting close to some number, let's say 2, for f of x, it's equal to some limit, and let's say maybe 5. And you've got as x approaches C for some g of x, it's equal to another value, let's say m. So we could still be approaching 2, but this time g of x, which is a different function, might have a limit of, let's say, -3. Okay, the following things have to be true. That if you do the limit as x approaches C for f of x plus g of x, that's just going to equal whatever the limit is for f of x plus the limit for g of x, which would be m. So it'd just be L plus m. That's called the sum rule. Kind of makes sense? That also works with subtraction. If you had the limit as x approaches C for f of x minus g of x, then that would just be the limit of f of x, which is L, minus the limit of g of x, which is n. That would be the difference rule. Okay. You also have one for multiplication. If you have f of x times g of x, you just multiply the two limits and get L times n. And that's your product rule. You have the limit as x approaches C of k, now remember k is a number, times f of x. Well, that's just k times what your limit was for f of x, which was L. That's called the constant multiple rule. Because if you have a constant times a function, you just multiply the answer times the constant. So we take the answer for the limit for f of x, which was L, and we multiply by the constant k. Then you have the quotient rule. If you have f of x divided by g of x, then you're going to get L divided by m But you have to make sure that you qualify that m cannot equal 0, because remember, division by 0 is bad stuff. So we talk about later what happens when you get 0 in the bottom in your denominator and how you do limits then. Then the last one is your power rule. You've got the limit as x approaches c of f of x to the n. That just says you take the limit, which was L, and raise it to the n. Okay, let's look at an example of this with some numbers so we can make sense out of it. Let's say we have the limit as x approaches 2 for f of x is, let's say, 5. And the limit as x approaches 2 for g of x is, let's say, negative 3. Then what would the limit as x approaches 2 for f of x plus g of x equal? Well, that would just be the sum of the two limits. It would be 5 plus negative 3, so that would just be 2. What about the limit as x approaches 2 for 3g of x? This is the constant multiple rule, so it's 3 times, what's the limit of g of x? And the limit of g of x was negative 3. So 3 times 3, negative 3, which would be negative 9. How about the limit as x approaches 2 for, let's say, 4f of x plus 2g of x? So now we're combining the sum and the constant multiple rules. So we do 4 times f of x, 4 times 5, plus 2 times g of x, 2 times negative 3. So I get 20 plus negative 6, which would be 14. And the limit as x approaches, let's say, 2 for f of x cubed would just be 5 cubed, which is 125. The main thing you have to be careful about is just remember that you only know what happens as x approaches 2. If I change the problem around and said, okay, what's the limit as x approaches 3 for, let's say, 4g of x? Well, I can't really tell you what happens as x approaches 3 because my information is only about as x approaches 2. Now, we can't put D and E, which stands for does not exist. What we can put is that it cannot be determined. Not enough information, something like that. Because you can't figure it out, but it doesn't mean that it wouldn't exist. Okay, last thing we want to look at just very quickly is how to solve limit problems algebraically. Those are actually the easiest. Let's say that I want to find what is the limit as x approaches 3 for 4x minus 2. Well, if I think of the graph of 4x minus 2, 4x minus 2 is a line. It's continuous. That means there's no gaps and breaks and holes and nothing weird's happening to your graph. We could sketch real quick. 4x minus 2 up 4 over 1. It looks something like that. And as x approaches 3, what's going to happen is, since there's no weird things happening in your graph, you could just substitute 3 in. 4 times 3 minus 2. 12 minus 2 would be 10. I would expect that if I pick a number like 2.9 and put it into that, I'm going to get an answer close to 10. If I were to pick 3.1 and put it into 4x minus 2, I would get an answer close to 10. So as long as my functions are nice and continuous, then all I have to do is just substitute in my values and get my limits that way. So let's say we had the limit as x approaches 0 for 2x plus 1 over 5x plus 4. So if I put in 0 for all my x's, I'm going to have 2 times 0 plus 1. That's going to give me 1 over 5 times 0 plus 1. So that's going to give me, or 5 times 0 plus 4, sorry. That's going to give me 4. So my answer would be 1/4. So that wraps up our beginning introduction to limits, and we'll work on some problems using these tomorrow.